Welcome everyone. Today we are going to explore a field called natural language processing, or NLP for short. NLP is a branch of artificial intelligence that focuses on helping computers understand and generate human language. You've already seen NLP in action. Whenever you're chatting with Siri, translating phrase using Google Translation, or reading auto-generated captions in a video, NLP powers a lot of tools. But today we will take a step deeper. I walk you through the key NLP building blocks. We will cover on how computers understand words using embeddings, how transformers revolutionized language models, and how to use pre-trained models like BERT or GPT to do things like sentiment analysis and question answering. We will also learn how to fine-tune these models to perform better on custom tasks. Each section will include hands-on examples, and I show you Python code that you can try later yourself. Whether you are aiming for AI context, research projects, or just want to build smart application, understanding of NLP and on how machines process language is a powerful skill, so I hope it will be useful to you. And let's begin by answering a basic question. How do we turn words into numbers, and how can we make a computer understand natural language? When we hear any word like cat, we understand what it means. It's a small animal, furry, often kept as pet, but computer doesn't know usually what language is and what is the words. It understands only numbers in some way. So we need a way to turn words into numbers somehow for computer to understand what are the similarities between them, what do they mean. So some meaningful way of translating words into numbers. That's what word embeddings do. They transform words into vectors that preserve semantic relationships. Words that appear in similar contexts ends up having similar vectors. For example, the word doctor and nurse are likely to appear near the same words like hospital or patient, so they get similar embeddings. There are two popular models for creating embeddings, Word2vec and GloVe. Word2vec learns by trying to predict a word based on context, or vice versa, so a context based on a word. It processes huge amount of text and gradually adjusts the vectors so that words appearing in similar contexts are close together in a vector space. GloVe, on the other hand, uses a matrix of word co-occurrence statistics, and it looks at how often pairs of words appear together in a corpus and derives word vectors that capture these global relationships. One amazing feature on embeddings is how they capture analogies. If you subtract vector man from king and add woman, the result is close to queen. So embeddings don't just represent words, they represent a relationship between words. Let's see how it works in practice. We will use Gensim library and especially Gensim downloader that provides an API to load models without loading their files. So let's start with downloading Word2vec model based and trained on Google News. So here you can see we downloaded a model. If you will try it yourself, it will take time. So be patient and wait for it. For me, it took kind of 3 minutes for loading it. So let's print what will be the result of most similar words of the dog. It will be dogs, puppy, pit bull, and so on. As you can see, it is quite similar to what a dog is. So it works quite good. And here you can see the probability of the dogs being similar to a word dog. So next example is the one that I previously already said. if we subtract a man from king and add woman, we will probably get queen. So if you see we are really getting a queen, we can see what was the other examples. So monarch, it is also close. So we can see some other examples. For example, similarity between car and bike is higher than between car and banana, and between car and engine, and so on. So, for example, car and sadness is too far away. So next one is GloVe model. It uses some other way of turning words into vectors. And here are some examples of using this model. For example, same similarity ones, and example with Paris, France, and Germany. So you can see that if we if we subtract France from Paris, and add Germany, we will get Berlin. But also we can get Frankfurt, as it is also a city in Germany. It works again, and we can see that here numbers are different, but still they are close. For example, as the GloVes use general context, for GloVe, car and engine and car and bike are in the same. They are similar in the same way, because they are usually in the same context. So we can visualize it. For example, here we made it. You can use this code and try to add here some other words. For example, we can add here some patient. And we can see that it will be somewhere near doctor and nurse, so it is quite accurate. But why can't we use these models like Word2vec and GloVe always? Here are some examples. For example, there is a word park. It could be park where kids play, or park where vehicle stops. And in this case, we will see that the similarity between them is like close to the equal. And in this case, if we will try to predict what is the word in some context, sometimes we will have some problems. It works for different words, and it can work for some like other examples, not only the work that are written the same. So let's go to the next step. How can we solve this problem? As you can see, the next topic is transformers. And transformers are the foundation of modern NLP models like BERT and GPT. And they changed quite everything by introducing a concept called attention. The key idea is that when understanding a word, context matters. So, for example, when we talk about park or about bus, the meaning will be different if we will talk about some like ocean and about the music. So traditional models often struggled with that. And Transformer used self-attention to fix it. Self-attention allows model to weight all the words in a sentence. When processing each word, it looks at every word from every other word, scores how relevant it is to the current word, and uses the scores to train a better understanding. This mechanism allows Transformer to understand both short-range and long-range relationships between words and do it efficiently in parallel. That's a huge step forward from older models like RNNs. And let's see how can we use transformers. So here you will find a helpful link if you want to dive deeper into theory. So first we installing the transformer library. It will also take time, and we want to download the BERT model. That was one of the first one and one of the most used models. And we download Tokenizer. It is a tool that will translate our words to embeddings. So we will take a sentence the cat sat on the mat. We will translate it to the embeddings using Tokenizer, and we will generate outputs using our model. So we will get attentions, and we can extract the last layer. Actually, the model is consist of a lot of layers of self-attention, and inside one layer we can have multiple heads. What does it mean? Each head learns to focus on different aspects of a sentence. For example, one head might focus on subject-verb relationships, and while another might look for named entities or punctuation patterns. The model doesn't rely on just one head because language is complex. Attention heads can specialize and capture different views on the same sentence. So when we average across heads in a single layer, we get a general picture of what a layer focuses on. When we look across multiple layers, we can see how model refines its understanding step by step. So let's see how we can visualize it. We can get attention matrix, the last layer attention, meant by heads, and we can have tokens that we put into our model. And there are also special indices, for example, end of the sentence, that we will skip for now. Later you can check it on Hugging Face on the documentation. You can just read through the documentation and find what is it. We filtering the attention to skip all the special words, and we want to show the heat map on how does the attention for the words looks like. As you can see, for most of the words, attention is the best for the same word. So when you trying to find what is the most important word in the full sentence, obviously it's the same word. So let's dive deeper into other words. It's obvious. So here are some easy steps on how to just skip the main word, and I just made the different heat maps for every word. So if we try to find what is the most important words for there, for some reason it's on. It's not really meaningful. But if we see what is the most important words for cat, it is there, set, and met. It's more meaningful from my point of view. Later on, I think it will be useful for you to search through the Hugging Face models and look how the layers usually looks like, how the attention usually looks like, and how to use it. So here are only few examples on the usage and on the representation of what how the models look inside. But I think it is better for you later to play with it and find some insights that will be meaningful for you. So, how can we use these transformers? First usage that I want to talk about is text classification. So, as it may be obvious from the name, text classification is about assigning labels to pieces of text. For example, when we want to find out if review is positive or negative, we can use sentiment analysis. If we want to understand if the message spam or not spam, or if we want to know what is the text about, for example, sports, politics, or tech industry, we can use classification. Text classification is widely used because it's simple to understand and easy to apply in the real world, and also it is a common task for AI competitions. Under the hood, a classification model reads the text, converts it to embedding, processes for transformer layers, and finally outputs a score for each possible label. The label will, with the highest score is selected as prediction, and you can use pre-trained model for this, and you can also train anything from scratch. Let's see some example of already pre-trained model. We will use Hugging Face. There is some pipelines on how to use it, and this is the library. At first, we will try sentiment analysis. We are loading classifier, and we are trying to classify the movie review. For example, here are some obvious examples, and as you can see, the result is positive for the positive one and negative for the negative one. So let's start with first task, sentiment analysis. You can just download the sentiment analysis through the pipeline library. So we are downloading it, and now we just can just use it. So we can input inside classifier some text, and it will classify it and score it. For example, in this case, we have some positive score, some positive, so some positive text for that derived in the movie, and some negative one. And as you can see, the model that is already fine-tuned in Hugging Face is really good with scoring these sentences. Next thing that you can try is emotion detection. For example, we can use text classification pipeline and especially BERT model for emotions, especially fine-tuned for emotions. And for example, you can use this sentence, and it will say that the label is joy with really high score. Next one, we can find some toxic comment detection. It is also BERT model, and in this case, you can also say that we find that it's toxic. Few more tasks is product review rating. For example, we can set some labels. For example, like how many stars should it be if it would be labeled with the star. In this case, it is a great review. That's why it is 5 stars. Next one, intent classification. But one more interesting example that you should see, it is multi-label classification. Some of the models can predict few labels, and in some cases we need not only one but more labels to be set to the sentence. For example, in this case, we can say for sure what is the emotion of this text, and we can ask to label all of these emotions. And as you can see, it is also a good example on how to use it. Actually, you can just go through the Hugging Face models and find a lot of classification models there. How to do it? You can just go to the Hugging Face site and choose models, and here you can choose, for example, text classification, and you will get a lot of different models that you can use. For example, toxic that we used already, for example, topic classifier that we can use for some classification of the texts. So, for example, here are some topics that could be classified with these models. So just using Hugging Face in this library, you can find any model you need, and most of them are open to use, so you can use any of them. It is also a good way to just go there and try some models, try to solve some tasks with them. And I think now it is good point to start talking about the pre-trained NLP models. You already saw how to use them, so right now let's talk about how are they built. So two of the most influential models that are used is BERT and GPT. You've already seen them in action without even realizing it, because most of Hugging Face pipeline use one of these under the hood. Let's start with BERT. BERT basically stands for bidirectional encoder representations from transformers. It reads a sentence both forwards and backwards at once. This is what we meant by bidirectional, and it is especially good for understanding context. It was trained with something called masked language modeling. This means it was trained to fill in missing word in a sentence. For example, if we hide word sun, in the sentence, the sun is something today. BERT can usually guess it correctly. This forces the model to deeply understand how words relate one to another. So here is the example of how can we use it. So we just using again pipeline and the task named fill mask, and the model, the basic BERT model. And if we try to fill the mask, it will give us some different answers. For example, the sun is something today, could be shining, could be rising, could be bright. So it's usually good at choosing the right word in between. And you can see the score. It's the you can use it if you want the most probable score, most probable word, or in some other examples. So let's go further. Next model is GPT, which stands for Generative Pre-trained Transformer, and it reads only from left to right, like how we naturally speak, right? And it is it was made for one particular reason. GPT couldn't see the whole text at once. It should read it one by one to be able to generate the text. So it's given a prompt and it can continue writing it in a coherent way. So BERT is basically great for understanding text, and GPT is great for generating text. Both of them were pre-trained on massive datasets like Wikipedia and books and so on, and can be fine-tuned for specific tasks like classification, like we saw before, or for summarization or for translation. Let's see them in action. We already saw how BERT was used. Now we can see how GPT-2 can be used. For example, we just use some prompt and it will give us some sentence. It sounds meaningful, and actually we can change parameters to make our sentences different. For example, we can make it more, for example, predictable or creative if we will change the temperature of the text. So lower the temperature, more focused and predictable will be text, and if we put higher temperature, the more creative and random will be text. So here is more predictable text, and here is more unpredictable. We also can change top K parameter. It will limiting our sampling to the top most likely next word. So for example, if we're talking about cosmos, it will unlikely to choose something about the food, for example. And in this case, we can make our model be more focused on the topic that we choose at the start. Here are some examples. Now we can go further. Next parameter we can use is top P. It's also about the predictability and the focusing. So it is how we usually can use our already fine-tuned model. So to summarize, BERT is a model for understanding tasks like classification, question answering, or sentence similarity, and GPT is the model that you can use for some generation task, for storytelling, dialogue, or for example, code completion. Both models have reshaped NLP, and both are freely available to use and fine-tune. And later we talk about fine-tuning, which lets you adapt this model on your own data and tasks, but for many cases, you can just use some already pre-trained versions of BERT or GPT. But before we move further, I will add here some additional links that you can use to read more about the BERT and GPT. For example, here you can read on Hugging Face, you can read about the initial GPT-2 model and about its usages, and I think here you will find some additional links that you can use, and also the same for BERT. And there are a lot more. If you want to dive deeper into the original papers, you can read them. So here are some links that is useful to read before moving forward. Let's now explore a powerful application of transformer models, question answering. In this task, a model is given a context, like a paragraph or document or some text, basically, and a question about something in that context. And the goal is to extract the correct answer as a subtraction from the context. It is called extractive QA. and it is used in everything from document search to chatbots and help desks. We will use BERT-based model that is fine-tuned on Squad dataset, one of the most popular benchmarks for this task. So let's dive deeper. We just again using pipeline, and we giving it a context about the Eiffel and about like dates and some historical info, and trying to ask when was the Eiffel built. And as we can see, the answer is correct, and that is because of the model was just really good fine-tuned on such tasks. But are there some problems with it? Maybe we can try to ask multiple questions for the big context. Let's try. We give a bigger text and try to ask few questions. And we can use it just using the simple for, and the result will be the same. The answers will be correct. Now, what will the model do if we will give her a context where there is no answer on the there is no right answer? In this case, it will guess something that sounds quite close to the question, and it is the point where problem starts. Because as you understand, if the model doesn't know, it will try to guess, and it will lie. So even really great models like GPT-4 that were fine-tuned on big data sets still will be lying, because it will still try to predict something from the context that it already has, even if it's not true, even if it's obviously not true, because for example, in this question, it is obvious for us that the Great Wall of China can be a designer of Eiffel Tower. So, if we will give the model empty context, it will break. So the context can be empty. And next one. What is good about these models? That it can give us long answers, like some legal stuff or some policies, so it can be really good for reading some documents that are written with hard that are hard to read by human, but for the model it is not really a problem. And it is really useful when you want to get a short form practical answer. For example, we have an info about the cafe, and we just need to know the exact time when this cafe is open. And these models can easily extract this answer and give us it in a form that we want. So these question answering tasks and models that are fine-tuned on this task are really helpful. We can use them, for example, in chatbots, in search tasks, and we should know about their limitations. For example, limitation that model will lie if the model doesn't know the answer. Now we know how to use the BERT and GPT models, how it powers tasks like classification or question answering. But what is the next step? The next step is to give these models an ability to make everything at once. And these are large language models such as GPT-4. Large language models are transformer-based models. They are obviously trained on massive datasets with billions of parameters, and it sometimes takes years to train one more model. GPT-4, for example, was trained on a mixture of web pages, books, code, and a lot of more. These models can understand prompts and generate long concurrent responses. But what makes them different from BERT or from GPT? BERT is optimized for understanding. It predicts masked tokens and it is great for classification and question answering. And GPT is optimized for generation. It predicts the next word and is trained in a left-right fashion, making it better to generate in long text. But GPT-4 is powerful because it can do a bit of everything. Answer questions, write stories, generate code, explain concepts, translate languages, and much more. And it does this using just natural language instructions and also called prompts. I will not give you some examples of using GPT models. I think you can do it by yourself just by using ChatGPT. But as you already understood, it is really powerful tool that you can use in everyday life, and that's why it is also a big problem to show it right now, because Collab will not be able to store such big models to generate something. That's why it is stored on some servers, and it is really hard to run it somewhere else. So, next step. What if we want to, for example, make this big model or some of the GPT or BERT models generate answer in some custom way. For example, we want them to not only answer the question, but say, for example, here is your answer, and then answering the question. In this case, we should fine-tune the model. So, what is it and how to do this? Obviously, the model has weights, and we can just give the model a little bit more information and just run training once again to fit the model. But it will take a lot of time and compute. That's why there are some ways to do it not straightforward. For example, we have LoRa. It is a method that where only small part of the model is fine-tuned, but most of it is frozen. Let's focus on LoRa. It is low rank adaptation. Instead of updating the whole model, it adds a few extra trainable layers called trunk decomposition matrices inside key parts of the transformer, like attention and projection layers. It saves memory, it saves training time, and it saves GPT usage. And it still achieves strong results on small and medium datasets. So how it works in practice? We should first take some existing model, for example, GPT-2. Then we should open tokenizer and define a prompt to check what was before and what will be after this prompt. Next, we want to have model LoRa. We are configuring it and taking some datasets that we want to train on, and then we are training it. So it is a basic pipeline of how to train LoRa. I will try to run it. Hopefully it will start. It will take, I think, a lot of time to train LoRa, even on a one epoch, but still it is a great great thing to have. Yeah, so one epoch will be running for 5 minutes approximately, and it won't be perfectly trained. Right now we are training on some Wikipedia texts, so the model will be able to write more huge and coherent texts. But if we make it only with path epoch, the loss will be still high and it won't be as great as we want. But still you can try run it for a longer time and see what are the results. So it is basically all that I wanted to show on this practical part. Today we saw a lot of different examples of large language models and just NLP models that are trained on not on that huge amount of data. We learned how words can be represented as vectors using Word2vec and GloVe. We explored some tasks like text classification, question answering, text duration, and fine-tuning. And we also saw a lot of lines of code that were using Hugging Face datasets and Hugging Face models. If you want to explore more on how to use it and how to what are possible usages of the NLP models, you can just go on Hugging Face and search through. There are a lot of additional information there. I will share with you this doc. Here are some useful links for transformer theory and for some other points that we discussed. So thank you for listening and have a great machine learning and AI journey.